Hello everyone, welcome back. In this video we're going to do the same plane 0, 1, 1, finding planar density, but for BCC crystal structure. Now drawing will be the same as we said that drawing the plane is independent of the crystal structure. So the plane that we have there for BCC, plane 0, 1, 1. This is plane 0, 1, 1. We said in order to do the rest of the calculation we need to specify the location of atoms. Since we have BCC, we have one at each corner, and one will be in the middle. Why? Because we know that there is one atom in the middle and this plane passes through the middle of the cube, so there will be an atom in the middle. Now again, we know that this edge is A and this is root 2A. Now let's specify or draw some cases to see which one will be true. Now first one, I'm gonna just draw them in a way to be so there's two there. There's the other two, and we have one will be in the middle. So this is the first case. So if this is true or not, we're gonna see it. Then the second one we're gonna do, so let's assume that this side is the A side. Now I'm gonna draw another case when the two atoms here will touch each other. Then we have the other two be somewhere here, and I'll be having one that's going to be in the middle. So we're going to manage in this manner. These two will be in contact in this manner, or we will have let's have them again. And the third possibility that I'm going to place it there, let's have them like this. So this is gonna now, let's say out of these three cases, which one will be the possible arrangement of atoms that we have it here? Well, we know A is equal to what in BCC? A is equal to 4 over root 3 R. So it means that the atoms, the two atoms will not touch each other. Why? Because A is more than 2R. It's more than 2R. So it's not going to be this one, because this is, if you consider this one to be A, it's 2R because they're touching each other. So this is not going to be this. Yes, it's possible to be this one, or possible to be this case here. Now, however, in this case here, the length of it is root 2A, Again, root 2a, we know that. So for root 2a, now we cancelled out this part here. It's between the first and the third one. So whether it's the first one or the third one. Now, root 2a, we have it here. So if you imagine this is going to be root 2a, yeah, it's going to be, there will be space between the atom. But there is space here, there is also space here. So both of them okay. We can assume that this is root 2a because there's a space between the atoms. But how do we choose between this one and the third one? The third one. Now, we will bring another information that we know in BCC. The diagonal, which we call the space diagonal in BCC, is equal to 4r. If you remember, the space diagonal in BCC 4r. What does it mean? It means that this atom with this one, they are touching each other. So there's supposed to be a link between them because this distance must be 4r. If it's 4r, so this is the case we have it here. Look, this is 4r, or this way is 4r. So the possible case that's going to be, it's this one, the arrangement of atom arrangement will be this manner. So if we draw the plane, which is from the center of the atoms, there we have it. There we can calculate, then we can calculate the atom, number of atoms. We said number of atom will be, there is quarter here, there is quarter here, there is quarter this corner, one full in the middle. So we have 4 quarters plus 1 in the middle. 4 quarters and 1 in the middle, which is going to be 2 atoms. 2 atoms. Well, the area is still root 2a squared, but a is equal to something. So if I want to write down the planar density, planar density, you write it equal to 2 atom over root 2a squared. Root 2a squared come from where? From a times root 2a. Then a, we know that it's equal to 4 over root 3r. So you can leave it with a square, or you can simplify it, whatever. Just here will be 16 over 3. Just putting this one in a bracket. Bracket is squared. You can go further to simplify it, leave it as this way. It is okay. If you have the atom radius, you'll place it here. Then you go to the planar density, and the unit we said that it's atom over nanometer square, or you can just write it nanometer minus 2. This is how we're calculating planar density. So first you have to draw the plane regardless of the crystal structure. Then you're going to use the crystal structure to see the atom arrangement, Then when you know the atom arrangement, you're going to draw the plane in this manner. By the way, this is how do you look at it? We look at it in this manner. We look at this in a perpendicular manner. That's why we'll draw it in this way. I didn't draw it in the inclined shape. We're looking at it in a 90 degree. So we draw the arrangement of atom to see which atom is touching what. Then we have the side of this plane. That's going to give us the area, and we calculate the number of atoms within it. Then we'll be able to calculate planar density. Now, the way that we explained family of direction, same thing is true for family of planes. Now, I can explain family of plane exactly here to tell you that family of planes still is the same as family of direction. Remember, family of direction, they had similar linear density. So when you see the family of plane, also they have same planar density. Now this is 0, 1, 1. 0, 1, 1. If I draw another plane with 101, a plane 101. This is the same family, yes? Remember family, what we said that? They have similar 2110, 2110. This is the same family, but let's prove it to see whether actually will be the same or not. So if I wanna draw this plane, the ABC, the intercepts that we have them, 1 over 1 will be 1, 1 over 0 will be infinity, 1 over 1 will be 1. So we're gonna draw this. This was the x-axis, we had it. And this is the y-axis. This is z-axis. So 1 in x will be here. 1 in z will be here. And it's parallel to y. So we're going to draw something this manner. We connect those two together. Then we say we draw a line parallel to y here. We draw another line here parallel to y. Then we connect together. If you don't know how to draw, watch the videos that we added on crystallographic planes. Now, this plane is also diagonal. Since we have BCC, we have the corner. We have the corner as well. One here, this corner, and one in the middle. Exactly the same combination we have it here. Why? Because this is A, and this side also will be what? Will be root 2A. Root 2A. So the area is the same, the atom arrangement is the same, the planar density will be exactly the same. Why? Because we call them family of plane. Those are family of plane. The same manner we explain the family of plane. So how do you represent family of plane? We'll say that planar density, we're going to use something like this, a curly bracket with 1, 1, 0, any family member of this combination, their planar density is equal to, what's going to be 16. Let's write it down because it's going to be 4 squared will be 16 with 2, 1 over 8 root 2, and this will be 3. So if 3 goes top, you can rearrange this one, will be, if I'm not wrong, 3 over 8 root 2 r squared. If you arrange this one, will be 16 here. That's going to be 3. So 1, that's going to be 8, and the 3 will go up, will be 3 over 8 root 2 r squared. This is basically this one. Come from here. Double check it to be sure that, but you can just rewrite this one. The planar density for a family of plane 110 means that any combination with 2 110 minus also is included will give you the same planar density. That's why we call them family of planes. Now, I will remind you something else. Now, family of plane, you understand that when you said family of plane, they have similar atom arrangement, similar planar density. Why? Because planar density means that they have similar atom arrangement there. Similar atom arrangement, we have it there. This is, we call them family of plane. A reminder to not confuse family with the equivalent plane. Now there is another term that we will use them that's going to be useful for us for the next topic when we have it. Equivalent plane. We said that since we have a crystal structure, and crystal structure, it's a continuous repetitive pattern. We said that it's a repetitive pattern. So if there is a plane here, for example, there is a plane here, you expect that this is a block. For example, this is a block. There is a plane here. You expect that plane to be available in the next block and available in the next block. And we show it to you that if you find even the Miller indices for this, all of them will come out 1, 1, 0. Why we call them? They are equivalent plane. They are the same. They are the same. we don't call them family, we don't call those family, we call them the same. Family will be what? Look, if this is a family, look, if I draw, this is family. Let's make a different color. Like this is a family. Why? Because the arrangement of atom in the blue one, when I drew it, or the one already drawn in the book, they are the same planar density they have it. So we call this one and this one together, we call them family. This one and this one for family. But those three, which is drawn there, three that drawn there, we call them equivalent plane. Why? Because all of them are exactly 110. 110. If I redraw this one, if I redraw the plane that I just drew it, this one, it's family, but it's not 110. It's not 110. This is going to be what? It's parallel to, no, it's coming for the origin. So it has to come here, it's parallel to Z. It's going to be 110. Sorry, this is going to be here minus 1. Yes, the plane of this one, that's going to be 1. For this one, 1 minus 1, 0. For example, this plane. I can draw another. This is family with this one. Why? Because the plane indices is 1 minus 1, 0. I have to shift the origin somewhere here. If I shift the origin here, that's going to be 1 minus 1, 0. So it is not equivalent with this one, but they are the same family. They are the same family. So two terms that we needed for the next topic we called XRD, X-ray diffraction, that we have to understand what do you mean by equivalent plane, equivalent planes. So the same plane, equivalent plane we call it, or family of planes. Family of planes means that they have similar atom arrangement, but they don't have the same direction. I mean, for example, this direction is different, but they have the same atom arrangement. We call them family members. So those two information will be required for the next topic that we have it, which we call it X-ray diffraction. We explain single crystal. This is an example of simple crystal happens in the nature. We explain polycrystalline. We said many metals come as a polycrystalline. We can explain these grains in chapter 4 in detail. Anisotropy, we explain the direction. We said that the direction that's gonna give us anisotropy. We said what? We said different directions give us different material property. I believe it was somewhere around here that we showed to you that materials, they behave differently in each direction, and the reason was due to yes, it's here, due to the density of the direction. So the same elements having different material property with different direction, we say we call this one anisotropy, which many material they are in anisotropic. We said that in engineering we will assume that they are isotropic. Why? Because we know that they come mainly in polycrystalline shape. The polycrystalline shape, it will help us to assume this manner that the material, they behave in all directions similar, even though we know that is not the correct way of assumption, but it's a good assumption and it's acceptable assumption that we using it throughout engineering and your life as a student. You're going to assume the material are isotropic, and then you're going to design whatever you're going to use the material for. So if I'm going to use a metal, let's say I'm using a metal for a design that I have it, I will assume that that metal is isotropic, means that in all direction it has similar behavior. This phenomena will be explained in chapter 6 in detail. We'll explain to you that when we're dealing with mechanical properties, we'll explain again that we assume that the material are isotropic, and what do you mean by this isotropic? We'll explain, will be clear in chapter 6 as well. So in the next video, we're going to explain about X-ray diffraction. How do we know if there is a crystal structure, and how do we know the crystal planes, the plane, and many more information with this technique we call X-ray diffraction. Thanks for watching.